Today, our topic is inverse functions. We've done some regular functions in 6.3, but now we're going to start on inverse functions, which you will love. The essential question for today: what are some traits of these so-called inverse functions? So, first off, let me just give you an idea of what inverse functions do. But before we get into an inverse function, let me just give you an example of a regular function. So here's my regular function, just f of x equals x cubed, a regular old function. I can do things with this function like make an xy table or an f of x table, and I could plug in some different values, so like -3. Hey, what's -3 cubed? Well, that's -27. What's -2 cubed? Well, that's -8. What's -1 cubed? -1. And let's do 0, 1, 2, and 3. So here's my table of values. I'm plugging in different x's. We know that this is the domain, and I'm putting them into the function and getting out different outputs. This is my range. Okay, so what is an inverse? An inverse takes the domain and range and flips them. So instead of inputting the domain, we're going to be inputting the range. Let me show you what I mean. For our inverse function, if I put something in, I'm actually going to call my inverse function g of x. 1 second. Okay, so my inverse function is the opposite. If I put a number in the range of the original function, I'll get a number out in the domain of my original function. So here's what I mean by that. If I input -27, I'm going to get out what? Well, -3. If I input -8, I'm going to get out -2. And so on. Do you see what's happening here? Basically, I'm taking numbers from the range of the original function, and they become the domain of the inverse function. So the domain and the range are flipped, and that's what an inverse function is. I take the function, I flip its domain and range. This inverse function, take a look at what pattern we see here. How do I get from -27 to -3? How do I get from -8 to -2? How do I get from -1 to -1? Well, it looks like I'm taking the cube root here, or taking it to the 1/3 power. Does this make sense that the inverse of x cubed is the cube root of x? So these are inverse functions. Their domain and range are flipped. So there's something else I can do with inverse functions. So that is make compositions of each other. So I have f of x equals x cubed. I have g of x equals the cube root of x. I know that these are inverses because their domain and ranges are flipped. Let's see what happens if I take f of g of x. Remember, this means I'm taking g of x and I'm sticking it into f of x. So instead of x cubed, I'm going to have the cube root of x cubed. I took g and I put it into the x in f of x. But what happens here? This is like x to the 1/3 cubed. I know here that these exponents need to multiply, so I'm left with just x to the first, or just x. Interesting. Let's also do g of f of x. Here I'm taking f of x, x cubed, and putting it into g of x, cube root of x cubed. And hey, doesn't the cube root of x cubed also equal x, because they're exact opposites? So I have this interesting property, and the interesting property is that when I compose inverse functions, when I stick one function into the other function, in either order, I get x. Interesting. By the way, this is analogous to if I were to add 2 plus -2 and get 0, or do 2 times 1/2 and get 1. If I compose inverse functions, I get x. So look, inverses with addition, inverses with multiplication, inverses with functions. And I get different things out depending on if it's addition, multiplication, or a function. In this case, when I compose functions that are inverses, I get x. Next, they're graphs. This is a little bit confusing. I don't know if we've looked at the graph of cubes or cube roots yet. This green function is the graph of x cubed. This red function is the graph of the cube root of x. And I drew in the line, the straight line y equals x, because these graphs happen to be reflected over this line. So here's your next fact about inverses. Inverses are reflected over the line y equals x. Over the line y equals x. And if you're not really seeing this, kind of tilt your head at a diagonal. That's what I'm doing right now. I don't know if my voice is changing. I'm viewing that y equals x as a mirror. And like whatever is on this side directly appears on this side. Whatever appears over here directly appears over here. It's like a mirror image of each other. And if you don't know really what I'm talking about, just stand in front of a mirror yourself. When you're far away from the mirror, your reflection is going to be far away from the mirror as well. When you're touching the mirror, you're going to be touching like your own hand's reflection. Does that make sense? So inverses are reflected over this diagonal line y equals x. Interesting. Finally, how do I find an inverse? If I don't just happen to know that the opposite of x cubed is the cube root of x, how would I actually find it? There's a very easy way to find the inverse function, and that is to flip the x and y and then solve for y. So let me demonstrate that here. Here, f of x is like y, right? Okay, so this function, I could write it as f of x equals x cubed. I'll write it as y equals x cubed for our purpose. So first step in finding the inverse, I'm going to flip x and y. So x equals y cubed. Everywhere I saw an x, there's now a y. Everywhere I saw a y, there's now an x. Second step, I need to solve for y. In this case, solving for y means I'm going to take both sides to the 1/3 power or take the cube root. Either one, same thing. Here this cancels and I'm left with just y equals x to the 1/3. And that's my inverse function, right? So this is my inverse. My inverse is x to the 1/3, which we already knew, but this is a way you can solve for it. So g of x, my inverse, is x to the 1/3. I flipped the x and the y, and then I solved for y, and that gave me the inverse. Okay, so let's try out some of these things on an example that we don't know. I know I've gone through a lot of stuff, but hopefully you're keeping it all straight, these little facts about inverses. So now we'll try. Okay, first of all, I have this function. This is a nice, easy function, but the inverse is not necessarily obvious. So the first part asks me to find the inverse of f of x equals 3x minus 5. So remember, how do I find the inverse? First, I need to flip x and y. Remember that f of x is like y. So if I'm flipping x and y, here I see a y, I'm going to write an x. Here I see an x, I'm going to write a y. And now my goal is to solve for y. And when I solve for y, that will be my inverse. So I'm trying to isolate y here. Let's add 5 to both sides. So x plus 5 equals 3y. And then I guess I would divide by 3. So divide every term by 3. I'm going to get y equals, I'll just write it as 1/3 x plus 5 over 3. This is my inverse function. So I'll write it as g of x because typically we use g of x to denote an inverse. My inverse function is 1/3 x plus 5/3. Now, let's prove my function is actually an inverse with compositions. Remember, if I put g into f, I should get what as the result? If they're really inverses, I should get x. Let's see if that happens. I'm going to stick g into f. So here's my original f, 3x minus 5. But instead of the x, I'm going to put all of g. So here goes g, 1/3 x plus 5 over 3. Okay, sweet. So this is f of g of x. I put g of x into the f. And let's just simplify some things here. What can I simplify? Well, I can distribute the 3 in. What's 3 times 1/3 x? Well, that would be just x. 3 times 5/3 is 5. I didn't deal with this minus 5 yet, so it's just over here. And now what happens with the 5's? Well, look, they cancel, and so I'm left with just x, which is exactly what I thought would happen, because when I compose inverses of each other, I'm left with just x. Super cool. Here are the graphs, if you wanted to know. Let's see, this top one is the inverse. G of x equals 1/3 x plus 5/3. This one is the original function, f of x, and it was, what was it again? 3x minus 5. And as you can see, I drew the line y equals x here, and it definitely looks like these functions are reflected. Like, look, when f of x is really far away from the mirror, g of x is also really far away from the mirror. When f of x is really close to the mirror, touching it, g of x is also touching the mirror. And I'll erase that picture quickly because sometimes things can get inappropriate while drawing circles. So, summary, inverses, they have domains and ranges that are swapped. So the domain of the original function becomes the range of the inverse and vice versa. Next, compositions. When I compose f of g of x or g of f of x, I am left with just x. And that's how I know that f and g are inverses. Inverses are also on a graph a reflection over the line y equals x. So if you see your two functions are reflected over this diagonal line, they are inverses. Finally, to find an inverse, you're going to flip x and y and solve, just like I did here. I put an x everywhere I saw a y, I put a y everywhere I solved an x, and then I solved for the y, which gave me my inverse. Guys, thanks for watching. Have a nice evening.